Hello, this is Mr. Waters, and good morning to you. And I have your tests, which of you sent back to me. I haven't, they're still in the grading lab. I haven't worked all the way through them, but I will be soon, okay? So by the time we're meeting again next week, those tests should all be graded. But in the meantime, we're going to go on with a new topic in applied calculus, and that is a topic called related rates. Now, the way I'm going to go at this topic, at least for today, is that we're going to break this up into a couple of different sort of short videos that please watch in order. Okay, just don't download the homework and start cranking away at it, because it might not go so, it's not the easiest way to do it, okay? And in this first video, all I'm going to do is I'm going to give you some situations, some scenarios in where we'll be solving related rates problems, to give you an idea of what kind of situations, what kind of problems we're going to solve and what we could use this for, and also to kind of introduce the vocabulary a little bit. So for instance, let's say that in our first situation, you've got a pool of water. So imagine the surface of the water is a pool of water, and you drop into it a stone. So you've got some water here, right? And into it, you drop a rock, right in there, and it bloop, like that, and it makes a bubble, and it makes a splash. And then, as the time goes on, from the center where you drop the pebble, you're going to see, well, the waves, the ripples, go outward from the center, right? And they'll come out, they'll expand outwards in a perfect circle, right? Now, what we want to get at is this. If we think of this circle of the disturbance of the water, where the ripples are, as having an area A, and we think of the boundary of those ripples as they go outwards, as we think of that boundary of that circle as having an R, you can see that as time goes along, as the area of the ripples get bigger, the radius will also get bigger at the same time, at a proportional rate. Okay, so in other words, the rate of change of the area, specifically in this case, the rate of increase of the area, is going to be related to the rate of change, or in this case, the rate of change of R, which is R primed. As the area of the circle gets bigger and bigger and bigger and bigger, you can see that the radius is going to increase proportionally, according to some proportion at the same time. This rate is related to that rate. Okay, does that make sense? So if we knew, for example, what this rate was, we would have a way, and we're going to be seeing how to do this, we would have a way of calculating that one there. Okay, so that's what we mean by related rate. We're going to be working with two rates of change. Generally in some kind of physical scenario like this, we're going to be given one rate, and we're going to be solving for the other rate. Okay, now keep in mind, this isn't an algebra problem. I'm not going to tell you, when R is equal to 8, what's the area? We're not going to be calculating static quantities. We're going to be calculating rates of change, which is going to involve, as you know, derivatives. Okay, which is why this is a calculus problem. Okay, so here's another one. Imagine, great artwork here. Hopefully you can see that's a sphere there, right? Three-dimensional circle. Imagine that is a snowball. Okay? Imagine this is a snowball. Okay? We love our snowball. We've been out in the snow. We're going to take our snowball and we're going to bring it inside. We're going to show mom and dad, oh, look, mom and dad, a snowball. Well, okay, of course, the snowball begins to melt on the counter, right? So there's two quantities here that are related to each other, okay? The volume of the snowball, right? And then also, of course, which is given by the amount of snow inside the ball, which is roughly spherical, okay? And then that's related to the radius of the snowball, right there, okay? And you can see that the algebra problem would be, if I tell you the radius of the snowball, you calculate using the formula for the volume of a sphere, which is roughly the shape of the snowball. You'd be able to tell me what the volume is. But that's not the problem we're going to be interested in, because we already know how to do that. Okay? Plus, it's not super interesting, frankly, or necessarily super useful to be able to do that. Here's the problem we do want to get at, is that the snowball's melting, right? That's one reason why we're not really worried about calculating the volume, because the volume's not a constant. As it sits on the counter and everybody in the family is sitting there admiring your snowball that you made, right? It's actually melting onto the counter, right? And so the volume is getting smaller and smaller and smaller, right? So we could specify a V primed, which is using our calculus, notation, dV dt. It's the rate at which the volume is changing with respect to time, which we can just call with our shorthand V primed, right? But keep in mind, just like the circle of water up here, ripples of water up here, we've got a quantity here that's changing with respect to time. Okay? All right, so that's how that goes there. Okay, so then that's related to, as the snowball melts, of course, we're going to have R primed. That's the rate at which the radius, in this case, is decreasing. Does that make sense? The radius is getting smaller, and so that's going to be, it's getting smaller with respect to time. So we're going to call that, using our formal calculus notation, dr dt. So both of these quantities, dV dt and dr dt, you can see that they're related to each other. They're proportional to each other. As one gets smaller, the other one gets smaller at some sort of predictable rate, right? Okay, but both of these, just like these up here, they're both actually changing with respect to time. Okay, so that's another one. Okay, we're going to do a couple of more. Then I'm going to let you go, and you should go on to the next video. It's actually going to be a PowerPoint. Okay, or I guess I'll just do one more here because I don't want to keep you too long just on the intro. Okay, so here's another one. Let's say we've got a rocket. There it is. Here's our rocket on the ground. It's up there, down at Cape Canaveral in Florida. And then, so we've got a rocket right there on the launcher. I'm going to call that L for the launcher, right? And then over here, there's going to be a person standing and watching the thing launch, right? So over here is going to be an observer, okay? And they're watching it launch. Well, you can imagine the rocket launches, and it shoots up into the air like that. Now, of course, it's not going at a constant speed. It's accelerating, isn't it? Right, as it goes upwards. Now, you can also imagine that our observer, better put that here. The rocket is now up here, you understand, right, after it's launched. And then the observer, obviously, because they're the observer, is over here watching the thing as it launches. Right? Watching a thing go up in the air. Well, this thing, as you can see, this rocket has a speed, right? Which is the velocity of the rocket. Okay? Well, let's say that the velocity of the rocket is, well, let's not worry about a number here. There's a velocity of the rocket there, right? Over here, the observer is watching the rocket there, and as the observer watches the rocket go upwards, of course, the person's eyes track through some angle theta, right? So we can, in this particular problem, for example, this rocket is going to have a distance above the ground, right? So we can see that as the distance increases, this angle is going to increase, isn't it? It's going to start out at 0, and it's going to get bigger and bigger and bigger and bigger as the height or the distance above the ground gets bigger and bigger and bigger and bigger, right? That makes sense? So the distance is going to increase with time. So that's going to be d primed, which is formally, you know what, I better call that a capital D so we don't have too many D's here. Let's call that vertical distance capital D. That's going to be d distance dt, the rate at which the distance or the height of the rocket is changing or increasing with respect to time. At the same time, this angle is increasing, isn't it? Okay? So theta, we're going to call it theta primed, and using our formal algebra notation, we've got two quantities here, which is d theta, or this quantity d theta dt. So these two are both increasing, and they're not directly related to each other. They're both directly related to time. They're both functions of time. So both of these are increasing with respect to time. How much this one is increasing in relation to that one is it's increasing in some predictable way. There's some predictable proportion. So these two are what are called related rates, or related rates of change. So we're going to solve problems involving, if I give you this one, how much is that one? And again, we're not looking for static quantities. We're not going to have a problem where if I tell you the angle is 30 degrees, how far above the ground is the rocket? Or if I know the rocket is 2 miles above the ground, what's the angle of the observer? Those are algebra trig problems, which we've done before, and that's not what we're interested in here. We want to know the rate. If this thing is flying upwards at a rate of, 100 miles an hour, at what rate do my eyes have to track upward in, say, degrees per second in order to keep track of it? That's the kind of problem we're interested in. Does that make sense? So these are related rates problems. There's lots of other scenarios, but those are just 3 to kind of get us started. Okay, very good.